Hi, and welcome to our discussion on atmospheric dynamics. We've covered a few topics already, and we're down to the mass continuity equation and the concept of mass continuity. So what we're going to do is we're going to look at how air flows through a volume and how in that volume the mass changes. So overall, you can say that mass is conserved. Mass can't be created or destroyed in the atmosphere, but it just moves from place to place. So we're going to look at three-dimensional space. We're going to look at a volume, and we're going to look at the air that's moving one side of that volume and air that's exiting the other side. And the mass of air that's coming in on one side may be different than the amount of mass coming out the other side. So if there is a difference between the masses going in and the masses coming out, then there must be a change in mass in that volume. That's your difference in mass. That means that mass is either piling up in that box or leaving that box faster than it's coming in. So what we want to do is figure out the change in mass in that volume of the box. To do that, we have to rely on some mathematics. And to do that, we're going to look at something that we call flux, meaning that how much mass is moving through the side of one of those boxes. So the mass that's coming in is a function of the volume that you're considering, and that volume has three sides. So we're going to look at one side. We're going to look at a side that has length and width, and we're going to call that side, that area of that side, where it's simply a multiplication of the length times the width. And the length we're going to call dy, a change in the y direction. And the width we're going to call dz, which is the change in the z direction. So we'll multiply these two distances, dy and dz. That gives us an area, and that's the area that the air is flowing through. So that's one side. Now the air is moving, and it's moving in the x direction, so that means that it's changing its x position with time. So that's dx dt. So we've got the dx dt, and we got the dy and the dz. Now you know that, of course, the air has a certain amount of mass, so it's moving along. And instead of mass per se, we're going to look at density. Remember that whenever we look at the atmosphere, it's hard to measure mass. It's pretty hard to measure density, but density is one of the terms in our equation, so we're going to use density. So that's mass divided by volume. And then finally, this is all occurring over a period of time. We want to see how much air is moving through that side over a period of time. So that's where your dt comes from. So here's our equation now. The mass coming in one side of the box is the density, rho, times the velocity of the wind in the x direction, which is u, times the area that we're looking at, the side, which is dy dz, and then finally the time. How long does it take for the air, or how long are we looking at a period of time of air moving through that side of the box? So that's the mass of air coming in. I know it looks pretty complicated. We could probably just use m, but that's our equation right there. Now, the mass coming out depends upon how fast how the air changes as it moves from one side of the box to the other. As the air comes in, it might be slowing down, so the velocity is changing. The u is changing in the x direction. And then the other thing is that the density of the air might be changing, so we have to put that in there also. So that's our change in the density and u over the x distance from one side of the box to the other. So that's how much the mass changes as it moves. So we got to include that into our equation, because by the time it gets to the other side of the box, the velocity or the density may have changed. So we have to, the air that's coming out the other side, the mass that's coming out the other side, is what came in on the left side, in other words, what came in, and the change. So we have to incorporate the change, and that would be the derivative of density and wind speed over a period, over a distance, dx, and then multiplied by the area side of the box that the air is coming out, and then over a period of time. I know this is getting pretty complicated, but we'll get simple here shortly. So this is what's coming in, this is what's going out. Take the difference and we figure out what's piling up, how much mass is being added or taken out of the box. So that's what we're going to do. We're just going to take the difference between these two, the mass coming in, the mass coming out, and that'll give us our change in mass. So mathematically, if we just do the algebra, subtract the two, and then also just distribute the terms, eventually we find that the change in mass is simply the change in the density and the u component of the wind over the x distance times x times y times z times time. So that's what's coming in, or that's what's being added as the wind moves in the x direction. That's what's being added or taken out of the box, the mass. We could also do that in the y direction. We could also do it in the z direction, and we'll get equations that are similar. So to figure out the total mass that was added or taken out of that volume, of that box, we just add the x, the y, and z directions together, and we get the total mass as a result of the wind flowing through that box three-dimensionally. So what we're going to do to this equation now is we are going to move the velocity derivative and the time derivative over to the other side. And we know that the mass divided by volume is density, so that gives us a change in mass over volume is density. And then since we're taking the derivative with respect to time, that gives us the change in density with time on one side. And on the other side is all of the fluxes, all of the changes as a result of density and the changes as a result of the wind component in both in all of the x, y, and z directions. So what we're going to do now is simply move everything over to one side. We're going to add the x, y, and z over to the left side. That means that on the right side, everything is equal to 0. So now what we're going to do is we're going to take out density. One thing that meteorologists do, typically we try and see what is the biggest change in the equation, because there's so many variables and it's hard to keep track of all the changes. Sometimes one change is so small that it's masked by the bigger changes in the other variables. So that's what's going on here. One thing is we found is that density changes are smaller than the change in the wind. So we're going to pull out density from the derivative in the x, y, and z directions. And then one other simplification we're going to make to this equation, and this equation is justified by theory and looking at which variables are most important. We found that the changes in density over time are much smaller than the changes in the wind speed in the x, y, and z directions. So I know this, we can't keep track of everything. It's pretty complicated. We got to simplify so that our concepts are a little bit easier to understand. So that's what we're going to do. We're going to get rid of density. I know it seems like a travesty, but we're going to do it anyway. When we do that, we're left with an equation that's a little bit more simple. It's simply the change of u in the x direction and the change in v in the y direction and the change in w in the z direction is equal to 0. So in other words, it says that the winds, as they change, their sum should equal 0. So we can move this around, this equation around a little bit, and what we have, we'll look at the horizontal motion of the wind and how it affects the vertical motion of the wind. And that's what we do in that last equation at the bottom. So actually, you've seen parts of this equation already. The du dx and the dv dy actually are divergence. And we talked about divergence in the kinematics section of this course and of these videos. The right-hand side of this equation, the dw dz, well, dw or w is vertical velocities, and the dz is the height. So this says that vertical motions changing with height are a result of divergence, or the opposite would be convergence. So basically what this says is convergence and divergence produces vertical motions, rising or sinking motions. The bottom equations that you see are just a little bit different way of showing divergence. Sometimes we don't like looking at the du dx plus dv dy. Instead, we want to use some shorthand notation. So that's what the equation on the left side of the bottom indicates. We just use a delta, a Greek letter delta, small delta, to indicate divergence. And then on the right side, the equation that you see there, the del dot v, is just a vector notation for indicating divergence. So what this shows here is all the different ways we can write the mass continuity equation using different forms of shorthand notation for divergence. Either we use the Greek letter delta, or we can use the vector notation del dot v, or we can actually write it out in terms of wind components u and v, and also the directions x and y. On the bottom three equations, we just move the minus sign over to the other side. Sometimes that's useful when we're trying to diagnose or figure out what's going on with this equation. I'm going to throw one more curveball at you, and that is that we can represent vertical motions in terms of pressure coordinates. And this was mentioned in a previous video, that sometimes vertical velocities are given in terms of omega. And what omega is the change in pressure with time. And we're going to spend more time talking about this later on. But this is the preferred method in meteorology to talk about vertical motions. It's using the Greek letter omega. So that's all we're going to cover for this lecture, and there will be another one to follow up.